So in this video, we're going to talk about when to use a table, when to use different kinds of graphs, etc. And so I call it finding the not wrong visualization. Now remember, effective visualization works with the human mind's ability to see, process, and think about information. And so what you want to think about this idea is that there are visual perception principles and visual perception programming for want of a better word in humans. And if you build a fit for purpose visualization, those two things, the more fit for purpose that the visualization is, as far as being fit for the kind of relationship that you're showing and working with visual perception programming within humans, we're going to have higher quantitative reasoning and hopefully higher understanding and insight. So what we're going to do for the rest of the day is start talking about how we determine whether we make how we make a visualization type fit for purpose. So it starts with finding a fit between the data you have, the kind of relationship that you're presenting, and the number of dimensions or categories that you need to tell your story. Remember back to that Hawaii heat map versus the line graph. Depending upon the story, one of those visualizations may have been better than the other. So when we're trying to decide how to get to a fit for purpose visualization, the first question should be, do I need a visualization at all? So when you're only presenting a couple of numbers, simple text might be fine, especially if you're giving a presentation. You might say quarter two sales were a million rupees, which was 15% higher than forecast. So the first question is table versus graphic. So assuming that we do need a visualization, we have to choose between a table versus a graphic, and tables are visualizations too. Okay, now in our visualizations, the message is going to be, we're going to basically have two kinds of data: quantitative information and categorical information. Now, just because something's a number does not make it quantitative information. It's the kind of data that measures something, the amount of a sale, the amount of profit, number of orders, count of help desk calls. But quantitative data is numerical, right? The key thing that you're going to try to decide is if it's quantitative information, it's information that you might do math with. You might sum them up, you might average them, you might subtract them, okay? So that's going to be your cue that you're dealing with quantitative information. Those are going to typically be in Tableau measures. The other kind of information is categorical information, which are usually the dimensions in Tableau. It's the kind of data that identifies what the qualitative values mean. So it's sum of sales by the category, by the product subcategory as a categorical variable, right? And categorical variables can be text or they can be numerical. All right, so the categorical variables are the things that you might slice and dice the quantitative variables by. So in this simple example, which parts of the graph are quantitative and which ones are qualitative? Take a moment to think about it. So when we look at this, there's actually, obviously the y-axis is quantitative. It's the amount of sales. This is not a complete graph. We don't know what these numbers mean. But let's just say it's sales, direct and indirect sales. We have an x-axis, which is categorical, because we're going to slice and dice these sales by quarter. And the bars are both categorical and quantitative. The height of the bar has a quantitative meaning. The division between the bars has a categorical meaning. So we have the direct sales for quarter one versus the indirect sales for quarter one. And so we see how these categories are slicing and dicing the data up into these different bars. The bars represent the level of that quantitative variable within that categorical dimension. So when choosing between a table and a graphic, your first question should always be, how will the information be used? And from your reading, tables make it easy to look up individual, actually, sorry, this is not from the reading. It's from a different view book. but the same thing's in Now You See It. Tables make it easy to look up individual values. So if the visualization is intended to help your user look up or compare a couple of very few individual numbers where they need precision to know exactly what the numbers are, you should willingly and quickly choose a table. One of the biggest problems that I see in student projects is there's often times where a group or a student should choose a table, but there seems to be this aversion in data visualization class to use a table. We have to remember that tables are data visualizations, and if the purpose is precision and looking up individual values, you should probably be looking at a table. Because when we start looking at graphs, we're going to lose some precision, and it's going to be harder to identify individual values. So choose a table when the display is going to be used. This kind of summarizes what I've just said. When the display will be used to look up for particular values, to compare individual values, but not groups or series of values to one another. Precision is required. Quantitative information involves more than one unit of measure. We'll look at that in a second. And both summary and detail values are included. Now, Few in the reading goes through several relationships in the table, quantitative to categorical, quantitative to quantitative. These things are an interesting taxonomy, but not especially meaningful as far as any real difference in how we create the table. It's purely, in general, it's purely a matter of interpretation. So between one set of quantitative values and one set of categorical values, we have our salespeople ranked here by year-to-date sales. We also could be doing one set of quantitative information, which is sales, and the intersection of multiple categories. Again, each time we add a dimension of a category to a visualization, we're basically choosing a different level of aggregation for the quantitative variable. This is quantitative to categorical, where we have one set of sales numbers, which is the quantitative variable, and we have a set of multiple hierarchical categories. And just notice, this is really no different. It's just a different, it's no different about what's happening. It's just different way that we are presenting the data. When you have a hierarchy of categories, you're going to present them on the same axis. You wouldn't put product category up and going left to right, and then product going up and down. This makes more sense because there's an actual hierarchy to the data. And then he calls this a different thing. He calls this one a quantitative to quantitative. And really what he's talking about, that this is exactly the same table as table 2. But what we're doing this is when he calls this quantitative to quantitative, is that we have a different purpose. Rather than comparing a salesman in January to a salesman in February, we're comparing numbers in one dimension or one level of aggregation. I find this distinction too sharp, too precise. I mean, obviously, Few knows more than I do, so there must be a reason he's doing this, but I find it, like I said, too fine of an edge, too fine of a cut here, all right? We're not going to talk much more about tables because you've been using them for a long time. And we probably won't talk much about the design of tables at all. But what I do want you to be able to do is willingly choose to use a table when the appropriate time arises for the use of a table. So once we've decided that we're not going to use a table, that we're going to use a graph, we have to really look at the idea of how are we going to do it. Now, we've talked about before that the maximum number of dimensions that we can do in a typical 2D XY kind of chart is 6. But when we're trying to design these visualizations, we don't actually have that many choices as far as what kind of things we can use visually. Now, obviously, we could use frogs like we talked about in the first session, but we don't really want to do that. We want to use In general, we're going to want to use arbitrary shapes so that the shape isn't communicating something in the choice of shape by using potentially stacks of frogs or stacks of people icons. We want the shapes to be data neutral, and the way we use those shapes, whether they're lines, points, bars, etc., whether we use those things, the way we use them, we want those things to denote what the data is saying. So depending upon the kind of relationship you're showing, we're going to be basically gravitating towards certain kinds of charts, right? Certain kinds of shapes in our visualizations. So you've probably done scatter plots, at least in your regression class in undergrad, if you haven't done it yet in your graduate work. But when we're talking about a correlation, a scatter plot with dots is probably going to be the thing that we want to use, right? Now, in the convention, when you're using a scatter plot, each dot represents one case. And so, for instance, in the Hans Rosling video, each of the shapes was a dot. It was a different shape, right? Sorry, different sizes of those dots. That meant one case for instance, a country, right? And scatter plots are perfect if you want to explore the relationship between two variables. So when we start talking about visualizing correlation, we're going to be focusing on that, on dots, right? Now, when I say these things, what we're going to be basically saying is that for each kind of relationship, there is a kind of bread and butter initial choice of a visualization that we're going to be focusing on, and that we're going to have to come up with a good reason that this isn't the right choice. So for in the future, when we talk about correlation, a scatter plot's going to be kind of our bread and butter. We should use this unless we have a good reason not to. Now, the next thing that we're going to talk about is lines, and all lines is dots that are connected, and in similar ways, the dot represents a case or a level of a variable at a certain, for instance, point in time. But those things are just connecting dots. The lines are just connecting dots together. And so when you connect those points together in a line, it visually transforms those data points into a single shape, a chunk that our brain will evaluate. And it's generally by convention, when you have a line, you're talking about a series of data points in a graph. But even then, you can create ducks with even a line. Avoid ducks. Okay, so with lines, you've seen them with trend lines, you see them with sales over time. We're used to seeing trend lines. It makes sense that when we're talking about time series, we're going to generally be talking about lines when the data is continuous, potentially columns when the data is not continuous, and then we're going to kind of move from there. And remember, obviously, a curve is a line too. So a bar is simply a line with a dimension of width. But bars mean something different than lines. Bars represent a single data point, usually a categorical data point. So it's the sum of sales by product. And by convention, the width of the bar remains constant across all bars, and that width of the bar has no meaning. There's only a few very special cases where you might look at bars of different widths, but it's almost never done because it's confusing. Remember what we talked about in some of the reading, that we always want to, if we're going to compare differences in level of one variable, we want to do that with differences in one dimension. So if we're looking at differences in sales, and we're going to graphically represent that, we want to look at differences in length of bars for differences in sales, rather than differences in area of two different squares of different sizes. So here's our bars, but you can still tell lies with bars. Here's our total instances of disease. I just made this up. These are just made up numbers, okay? So a bar is actually representing the same thing as a point, so why would we use it? So think about if you just put dots here, and in this graph it's not that big of a deal, but if you had a bunch of maybe 20 or 30 categories, it's really hard to tie the dots back to the labels. And so one of the things we can do is just have this bar as being a way to tie the level of the variable back to its label. Oops, sorry. And the weight of the bar also makes it easier to compare the points to each other. And again, you can easily turn bars into ducks. Here's a sales by region chart. Again, just some random data. How have I turned this into a duck? Or at least turned it into a lie? You can see here that the differences in the regions are substantial, but they're not orders of magnitude different. Our lowest one's about 325,000. Our highest is about 400,000. And so there's maybe a difference of about 20% between these. I'm just, round numbers. But this graph shows a much different picture. And who probably created this graph? Probably whoever's in charge of sales in the North region. And what did that person do? That person changed the x-axis to start at 300,000 rather than 0 and created lie factor. Instead of a 20%, or I guess it was 310,000, instead of about a 20% difference in level, we actually have a 1, 2, 3, 4, 5, 6, 7, 8, 9 times difference in level between west and north. So the effect in the data is much smaller than the effect in the visualization, so we've created lie factor. It gets worse with 3D. We've started to talk about 3D. We'll talk about it a little bit more later today. But 3D is always going to, what are we doing with 3D in these kinds of visualizations on a computer screen? We're tricking the eye to think that it's three-dimensional. And we're doing that by using more pixels at certain areas of these bars than in others for the same difference in data. So we're using fewer pixels in this graph to get from 0 to 50,000 than we are to getting from 350,000 to 400,000. It's even worse now when we do the lie chart, right? So anyway, the 3D is usually a problem. We're going to get into some more problems with 3D in a second. So I probably overstated this. The value axis should always start at 0 if you don't want to introduce lie factor. If you're not going to start the value axis at 0, you need to give the viewer significant cues that the axis is not starting at 0. And the 2D format of the bar already kind of overemphasizes the difference between points. We trade that off for the ease in being able to tie it back to the label, and 3D makes it worse. So we can also use boxes like a box plot. This is actually one of my favorite representations of data because a bar chart can tell you a whole lot, right? The bar shows the full distribution of values from the third quartile to the bottom first quartile. And the black line, the line here shows the median, the center of the distribution. And when you look at these three bars, they tell really different stories, right? And when we build these in Tableau, we're going to see how really different bar charts, especially with whiskers, can tell really different stories about distributions in a very small number of pixels. So where are we so far? We've talked about this kind of for the last couple sessions. Visualizations are cognitive aids. Visual perception is powerful. But lots of visualization packages, Excel for one, and again, I've said this several times, I was the greatest offender in this case, in this kind of thing, that Excel entices you to negatively influence perception by creating decoration and things like 3D because, oh, look, it looks so cool. I can do a 3D chart. So we want to really focus on simplicity. As some of the readings have talked about, usually the simplest graph may be the best, right? We don't want to focus on style over simplicity, over fidelity of the data, unless there's a really good reason and we know what we're doing by moving to style instead of substance. We want to use solid, consistent shapes, single color, no gradient. We want our dimensions to be proportional to the effect of the data. And we want to try to always be thinking is how is this graph increasing cognitive processing ability of the viewer? And no chart junk. We want to look for ways to increase the data content of chunks, as we talked about in a previous session. We want to make kind of these meta chunks where we use multiple points in multiple dimensions, turning multiple points and dimensions into a single chunk, and make it easy to compare by using single dimensions of difference in the visualization to match the number of dimensions, the single dimension difference in the data. Again, we choose a table when individual values are most important. We're going to choose a graph when the relationship between multiple values are more important. But you have to understand your relationship and your data type. So often, new visualizers find it difficult to really kind of, in some cases, I mean, some it'll be when you say, oh, I want to do a trend for the last 5 years of sales, everybody kind of knows that's a time series. But sometimes it's less easy to see that, exactly what's going on. And I always encourage my students to write out what you want the message of the visualization to do in words. And when you look at those words, you're going to be able to identify which of the relationships that we're going to be talking about in this class we're probably working with. Time series, ranking, part to whole, etc. And this is in the reading, so I'm going to kind of go through it kind of quickly. But for each of these relationships, there's a definition, and there's these key terms to be looking for. So if you write out your description and you see terms like change or increase or growth or trend, you're probably talking about a time series, because that time series is a series of values of quantity obtained at successive points in time, right? Usually with equal interval durations between them. And so that's the kind of data that you can actually find out things like change, increase, decrease, trend, right? So definition is an arrangement according to rank. Well, it's kind of, for ranking, it's some of these definitions are a little bit intuitively obvious. But when you're saying this is larger than, greater to, less than, highest performer, these kinds of things are going to be talking about rank. And ranks are really just a specialized version of part to whole. And a part to whole is simply the relationship of a proportion of a whole to itself. And when you hear things like rate or percentage of total, share, accounts for X%, you're probably talking about part to whole. And remember, when we get to talking about this, we're always going to want to show the whole so that people are comparing the part to the whole, not just to the other parts. And I'm going to get to the rest of these next week when we start talking about doing these in Tableau. So I'm just going to kind of skip through these. These slides are posted. And we're going to compare, we're going to do these in depth over the next couple of sessions.